let us try to learn about DC to AC inverters. In one of the very earliest lectures, we have seen that the 4-switch circuit, bridge circuit, can perform all sorts of power conversions, which includes DC to AC conversion also. The same circuit is shown here for quick reference. In fact, this is still one of the most popular inverter circuits used. And this is a single phase inverter circuit where we have 4 switches, S1, S2 and S3, S4, and there are 2 AC output terminals, A and B. And how do we get these terminals? 2 switches are connected in series, S1 and S4 are connected in series, and the midpoint of that connection is taken as one AC terminal. Similarly, other 2 set of switches are connected in series and the midpoint of the connection is taken as another AC terminal, that is B. So if you want to generate AC voltage, what do you mean by AC voltage? Based on the notion of AC that we have defined earlier, we want to generate a voltage of zero average value. Of course, it should be periodic to have a zero average value. So we will keep S1, S2 on together for some time and S3, S4 on together for the same amount of time, because if you keep S1, S2 on, the output voltage VAB will be equal to VDC, and if you keep S3, S4 on, the output voltage will be equal to minus VDC. So VDC and minus VDC applied for equal intervals will cause an AC voltage to be applied across the load. That means the voltage having zero average value being applied across the load. But how do we decide on the intervals? Like how long do we want to do this? How long do you want to switch S1, S2 on and S3, S4 on? It depends on the frequency. For example, we want to generate a 50 Hz AC voltage. We need to turn on S1, S2 for 10 milliseconds if we want to generate a square wave, and S3, S4 on for again 10 milliseconds, and again S1, S2 on for 10 milliseconds, and we keep on doing it. By doing so, we generate a square wave AC voltage across the load. Now we need to understand, is this what really want? Is this the kind of AC voltage you want to generate? Let us say we assume that we need to generate sinusoidal voltage. But why? Why do we need to generate sinusoidal voltage? We have generated a square wave AC voltage. What is the problem with it? The problem with the square wave voltage is that it has all sorts of harmonic components. It has 50 Hz. If you turn on and off the switches for 10 millisecond alternatively, you will have a fundamental component of 50 Hz, and it will also have a third harmonic, which is 150 Hz. It will have a fifth harmonic, 250 Hz. It will have seventh harmonic, 350 Hz, and so on. It has all odd harmonics. But are these harmonics useful? As per our earlier discussions, harmonics do not contribute to net energy transfer. That is why we don't want harmonics to be present in the waveforms. Let us try to understand this in a closer manner for this particular example. Let us say we represent our load with an RL. Because on the AC, in an AC circuit, you can have loads represented by resistors, inductors, capacitors, and combination of resistor, inductor, capacitors, voltage sources, and so on. So let us take the case of RL. So in this RL circuit, on this RL circuit, we are actually impressing a square wave voltage. That is what is happening. So this point is A and this point is B, let us say. So as we know, when we say we are applying square wave voltage, we are actually applying sinusoidal voltages of infinite order. So we have many sinusoidal voltages that are being applied, and what are the most significant ones? 50 Hz, 150 Hz, 250 Hz, and so on. Now we know that from superposition principle, we can arrive at the frequency components of this current. And why do we need to arrive at the frequency components of current? Because we have been thinking about net energy transfer. And we know that net energy transfer will happen when you have a corresponding frequency current for a given frequency of voltage. Let us see whether we have a corresponding frequency current for a given frequency of voltage here. We have a, let us take an example, 50 Hertz. The square wave has 50 Hertz component. So the current will have a 50 Hertz component. The square wave has 150 Hertz component. The current will also have 150 Hertz component. The square wave has 250 Hertz. The current will also have 250 Hertz component. Because it's a linear circuit, you have one component of current corresponding to each frequency of voltage. And obviously, this voltage and frequency at the same frequency interact with each other to produce certain average power. That means harmonics do also contribute to energy transfer when your circuit is like this, R and L. And what is happening to this net energy that is transferred? It is simply getting dissipated as heat. It is simply getting wasted as heat in this R. Even if you remember the DC-DC converters, when we say we connect a resistor at the output of a DC-DC converter, that doesn't mean that we are wasting the whole energy as heat in this resistor. This resistor is representing the system, or this resistor is representing the complete load that is seen by the DC-DC converter. Because ultimately energy has to be transformed to work, then only it is getting used properly. If the work is heating, then the representation of resistor alone is fine. But in many cases, many applications, the work may not be only heating. The work may be motion, which is a form of mechanical energy, or the work may be some kind of chemical energy that is being stored in some element. So it is not necessary that always we have this RL kind of representation in AC circuits. In fact, in most of the AC circuit applications or AC loads, we have an voltage source also. We have a voltage source also. This is now back EMF. Okay, this is known as back EMF because the majority of AC loads are motor loads. And motor loads can again be represented as RL, E. We are already familiar with this type of load. For a DC machine, for a DC motor or DC machine, this back EMF will be constant, but for an AC machine, this back EMF EB will also be varying. And how does it vary? In most of the machines, it varies as a sinusoid. But in some machines, it varies as a trapezoid. We are considering the case of this sinusoid. Because when it is a trapezoid, of course it has harmonics. So if you connect a voltage source, for example here, if you connect a voltage source, square wave voltage source, which has 50, 150, 250 and all that, and let us say if this back EMF is only 50, then we can easily say that our current flowing in this circuit should be as close to 50 Hertz as possible. Why? Because any other type of current is not going to do any work. And what do you mean by work? Net energy that is being transferred to this AC source. So this AC source is the receiver of energy. So the square wave source is delivering energy and this back EMF source is receiving energy. And in motors, the average power received, the P average, let me call B, P average of B. Average power received by this source, AC source EB, is actually equal to the mechanical work done, which is force times velocity in linear motion, torque times angular velocity in rotatory motion. So when we have this 50 Hertz source representation of the work done, see, the work done is now represented as a energy received by an AC source which is at 50 Hertz, and that is why we are interested in looking at only fundamental components, and we are interested in minimizing the other components which are harmonic components. Moreover, even the 50 Hertz fundamental component, we want it to be controllable. Why? Because by controlling this 50 Hertz component, we can control the energy transfer. How much energy is getting transferred? It depends on the relative magnitudes and relative phase angles of these voltages, because we are looking at the power flow between two AC sources, right? And one of them is almost a sinusoid, and one of them consists of all sorts of sinusoids, which is a square wave. So the two objectives are there. One objective is that the 50 Hertz component of the square wave or any AC voltage that you are generating with your inverter should be variable, and all other components, harmonic components, should be as small as possible, minimized as small as possible. Remember, these two objectives hold good for the case of EB being a pure sinusoid. But if EB is having any other components, for example, EB has 150 Hz also or 250 Hz also, then naturally we do not want to nullify the 150 Hz and 250 Hz components from our AC source, so that even those components will participate in energy transfer. For example, you take the case of trapezoid. The trapezoid has again third harmonic. The trapezoid has fifth harmonic. So we need not nullify the third harmonic and fifth harmonic of our AC voltage that we are generating with the inverter. We want to nullify the harmonic components, or we want to minimize the harmonic components only if we have a pure AC source to which the energy needs to be transferred. As most of the motors have almost sinusoidal back EMF, we will be considering the primary objectives of our inverter as controllable fundamental component, generating an AC voltage of controllable fundamental component, and generating an AC voltage with as less harmonics as possible. These two are the main objectives for our inverters to achieve.